everyone. Today I, Jyoti of class BSc Chemistry Honors first year, is here to read a chapter Chemical Kinetics of Physical Chemistry, and here we go.
Chemical kinetics. Chemical kinetics is the branch of physical chemistry which deals with the study of the speed of chemical reactions. Such studies also enables us to understand the mechanism by which the reaction occurs. Thus, in chemical kinetics, we can also determine the rate of chemical reaction. From the kinetic standpoint, the reactions are classified into two groups. First, homogeneous reactions which occurs entirely in one phase. Second, heterogeneous reactions where the transformation take place on the surface of catalyst or the walls on the container. Rate of reaction. The rate of reaction, that is the velocity of reaction, is the amount of a chemical change occurring per unit time. The rate is generally expressed as the decrease in concentration of the reactant or as the increase in concentration of the product. If the C concentration of reactant at any time T is the rate dC upon dt, or in the concentration of a product X at any time T, the rate would be dx upon dt. The time is usually expressed in seconds. The rate will have units of concentration divided by time, and the concentrations are taken in gram moles liter, hence rate is in moles liter per second. Factors influencing the rate of reactions. Rate of chemical reactions is influenced by the following factors: first, temperature; second, concentration of reactants; third, nature of reactants; fourth, catalyst; and fifth, radiations. First, temperature. In most cases, the rate of reactions of homogeneous reaction is approximately doubled or tripled by an increase in temperature of only 100 degrees Celsius. In some cases, the rise in reactions rates are even higher. Concentration of reactants. At fixed temperature is the absence of catalyst. The rate of given reactions increase with increased concentration of reactants with increasing concentration of reactant. The number of molecules per unit volume is increased, thus collision of frequency is increased, which ultimately caused increased reaction rate. Nature of reactants. A chemical reactions involve the rearrangement of atoms between the reacting molecules to the product. Old bonds are broken and new bonds are formed. Consequently, the nature and the strength of the bonds in the reactant molecule greatly influence of the rates of its transformation into products. The reaction in which involve lesser bond rearrangement proceeds much faster than those which involve larger bond rearrangement. Fourth, catalyst. The rate of chemical reaction is increased in presence of a catalyst, which ultimately enhances the speed of chemical reaction. Fifth, radiation. The rate of radiations of chemical reaction increase when radiations of specific waves length are observed by the reacting molecules. Such reactions are called photochemical reactions. For example, chlorine may be mixed safely with hydrogen in dark, since the reaction between two is very slow. However, when the mixture is exposed to the light, the reaction is explosive. Next, order of reaction. The order is the number of concentration terms on which reactions rate depends. Thus, if the rate of reactions depends on the first power of concentration of reactant, that is rate is equal to Kc1, the reaction is said to be the first order. When the rate is proportional to the product of two reactant concentration of square of the concentration of a reactant, the reaction is of second order. For example, the decomposition of hydroid iodic acid rate is equal to Kc2Hi, rate is equal to Kc2Hi, and the hydrogen iodine reaction is H2 plus I2 is equal to 2Hi. Rate is equal to KcH2Ci2. Here both are of second order. If the reaction rate is experimentally found to be represented, that is minus dC upon dt is equal to Kc power n. The order of the reaction is n. If several reactants A, B, C, R, etc. are involved in it and it is observed experimentally that the rate of process is given by minus dC upon dt Kc alpha A, C beta B, and C gamma C. Then the order of the reaction would be n equal to alpha plus beta plus gamma plus etc. This reaction is said to be alphath order with the respect to A, bth order with respect to B, etc. But there are reactions in which the order is fractional, n equal to 1 by 2, 3 by 2, etc. For example, the orthoparahydrin conversion, its rate is expressed by. Now, molecularity of a reaction. The molecularity of a reaction is defined as the number of molecules or atoms which take part in process of chemical change. The reactions in said to be unimolecular, bimolecular, and T-molecular. ठीक है, according to 1, 2 or 3 molecules are involved in the process of chemical change. The term unimolecular was used of all first order reactions, the term bimolecular for second order reactions, etc. Zero order kinetics. Chemical reactions whose rate does not depend on the concentration of reactants is called a zero order chemical reactions. The rate of reactions can be written as dx upon dt is equal to constant, that is dx upon dt is equal to k, dx equal to k of dt. On integration, both side integration dx equal to k integration of dt, x is equal to kt plus z integration constant, t equal to 0, x equal to 0, and hence z equal to 0. X is equal to kt, k equal to x upon t. A plot of x versus t should give a straight line passing through the origin as shown in the figure, and the slope of this straight line is k. Example, photochemical combination of H2 and Cl2 to form HCl. Now, first order kinetics. First order kinetics. A reaction of first order is represented as x is to y, where x is the reactant and y the product. The rate of reaction will be directly proportional to concentration, that is dc upon dt is equal to kc, in which c is the concentration of reactant at any time t and k is constant called the velocity constant or speed specific reaction rate, that is dc upon dt is equal to k of dt. On integration of dc upon c is equal to k integration dt. In c equal to kt plus z integration constant, if at the start of reactions initial concentration of the reactant is c0, then we have t equal to 0 and c equal to c naught. In substituting c naught is equal to z in c equal to kt minus in c0, c upon c0 upon c is equal to kt, or c equal to c0 e minus ki power kt. The concentration C therefore diminish exponentially with time. We may also write C naught minus C is equal to C naught bracket 1 minus k t bracket close. The rate equations may be also conveniently expressed in alternative form by x pressing the rate of in terms of product. When x moles per unit volume of product y is formed from the reactant, the concentration of reactant is A minus x, where A is the initial concentration of the reactants. Now its characteristics. In first order reaction, C equal to C naught E minus KT, the reactions cannot be completed because C would become 0 at infinite time. The second, the quantity A upon A minus X or C naught upon C is a ratio concentration, so its value will be the same whatever units are employed to express the concentration. Example, moles, liters, grams, and c etc. It shows the velocity constant K is equal to 1 upon T in A upon A minus X will have the dimensions of reciprocal times second inverse. Third, the equation is in A minus X is equal to minus KT in A. Log A minus X is equal to minus K upon 2.303 t plus log A. If log A minus X is plotted graphically against time, it would have given a straight line. So when a plot constructed from experimental values of log A minus X and t is found to be linear, the reaction of the first order, the slope of line is minus K upon 2.303, from which the velocity constant K can be determined. Fourth, the time required for half of the reactant to change be easily evaluated. Let t 1 by 2 is equal to time required when x equal to a by 2. T equal to half of is equal to 1 by k in a upon a minus 1 by 2. 1 by k in a upon a by 2 is equal to 2.303 log 2 upon k, that is 0.693 upon k. The period of half decomposition is thus constant for a given reaction and it is independent of initial concentration. The time required is called half value period or half life in case of radioactive changes. The time necessary to complete any definite fractions of reaction is independent of the initial concentration in first order kinetics 4. Now second order kinetics. A reaction will be of second order kinetics when the rate would depend upon the two concentration. Second order reactions are of two types. The rate is proportional to the square of the same reactant concentration. The rate is proportional to the product of two reactant concentration. The rate is proportional to the square of same reactant concentration. Let us say 2A is equal to products A minus X. If the two substances have same initial concentration A, if X denotes the concentration of reactants which disappears in time t, then the rate will be dx upon dt is equal to k into A minus X ka square, and dx upon A minus X ka whole square is equal to k dt. Integration both side. Now dx is equal to A minus X ka square is equal to k of integration dt. 1 upon a minus x is equal to kt plus z integration constant when t equal to 0, x equal to 0, and 1 upon a is equal to z. Substituting the value of z, 1 upon a minus x minus 1 upon a is equal to kt, velocity constant is equal to k is equal to x upon a t upon a minus x. Hence at any time t, fractional extent of the reaction would be x upon a is equal to 1 minus 1 upon 1 plus kTA. In second order reaction, when the two initial concentrations are of the same form, from the half of the value period is given by t half t1 by 2 is equal to x upon a k a minus a by 2 is equal to a by 2 into a into a into k into a by 2 is equal to 1 by ak. That is the time required for the half amount of reactant to undergo the changes inversely proportional to initial reaction a, whereas in first order reaction t 1 by 2 is constant. Second, the rate is proportional to the product of two reactant concentration, let us say of another type of reaction, a plus b is equal to product, that is a minus x and b minus x. When the initial concentration of two substances participating are different, say a and b, then the rate is given by dx upon dt is equal to k into a minus x and b minus x, where x is the amount of reactant transformed in time t. Dx is equal to a minus x upon b minus x is equal to k dt. 1 upon a minus b is equal to bracket start 1 b minus x upon minus 1 upon a minus x dx is equal to k dt. On integration 1 upon a minus b, integration dx upon b minus x minus 1 upon minus a minus b, integration dx upon a minus x is equal to k integration dt. In 1 upon a minus b in b minus x plus in a minus x is equal to kt plus z integration constant, or in 1 upon a minus b in a minus x b minus x is equal to kt plus z, where t is equal to 0, x is equal to 0, therefore 1 upon a minus b in a upon b is equal to z. Substituting 1 upon a minus b in a minus x and b minus x minus a minus b in a upon b is equal to kt, k equal to 1 upon t into a minus b in b into a minus x and a b minus x upon. It may also be written as t is equal to 2.303 upon k a minus b and log b a minus x upon a b minus x. The plot of log b a minus x and a b minus x against t for such reactions would be linear. The straight line would pass through the origin and from its slope 2.303 k a minus b, the velocity constant will be obtained. Now pseudo unimolecular reactions. There are many molecular reactions which follow the first order kinetics, though more than one kind of reactants involved in this reaction. Common examples are inversion of cane sugar or hydrolysis of ester in acid medium, that is C12H22O11 plus H2 is equal to 26H12O6, and next is CH3COOC2H5 plus H2 is equal to CH3COOH plus Ca2H2OH. These are truly second order reactions. Two substances, water and cane sugar or ester, participate, but the rate of reaction is experimentally observed to depend only the concentrations of sugar or ester. A second order reaction is governed by equation 3 if the concentration of one participant is very large compared to others, say B is greater than A, then B minus X is similar to B and A minus B is similar to minus B, which is practically constant, and equation 3 reduces to KB is equal to 1 upon T in A upon A minus X, or K dash is equal to 1 by 2 in A upon A minus X. Thus is under circumstances the reaction will follow first order kinetics. In these reactions water is present in such large excess that even the reaction is complete, the concentration of water would virtually remain unaltered. Minus dc upon dt is equal to kc sugar, CH2O is equal to k upon c sugar. Thus these reactions follow first order kinetics. This type of reaction is called pseudo and unimolecular reaction. Specific reaction rate first order reaction k is equal to minus dc upon dt upon c, hence dimension of k is mole per liter per second upon moles per liter, that is second inverse. The for second order reaction k is equal to minus dc upon dt c square, and dimension of k is liter, mole inverse and second inverse. In general units, k for a reaction so nth order would be given by moles liters second upon moles liter, power n is equal to liters, n minus 1 mole 1 minus n second inverse. Now catalytic reactions. Definition. Catalysis is the process of enhancing the rate of reactions by means of a foreign substance which remains unchanged in mass and chemical composition. Classification. Homogeneous catalysis. Homogeneous catalysis is where the catalyst and the reactant constitute in a single phase Heterogeneous catalysis is where the catalyst and the reactant constitute separate phase. Homogeneous catalyst example is nitric oxide is the oxidation of carbon monoxide to carbon dioxide. H positive ions act as a catalyst in hydrolysis of esters or sugars. Mechanism theory, intermediate compound formation theory. Substrate S reacts with catalyst producing an intermediate compound X. The intermediate compound then reacts to produce the product P along with the catalyst C. Moreover, the intermediate compounds also decompose to produce the substrate along with the catalyst. Scheme S plus C upon K1 upon K2 into K3 is equal to P plus C. Kinetics, the rate of formations of the product for the intermediate X if we invoke the steady states postulates. Now we substitute the Cx in equation 1.1, that is, now comments. It is clearly shown that the rate of dependence on catalyst concentration Cc for a given concentration of catalyst dCp upon dt, that is equal to K upon Cs, where K upon is equal to Kc upon Cc, that is K upon is proportional to Cc. The constant Kc is known as the catalytic coefficient for the catalyst. Characteristic, the catalyst remains unchanged in mass and chemical composition at the end of the reactions. A very minute quantity of catalyst can produce an appreciable effect on the speed of reactions. A catalyst cannot start a reaction but also increase its speed. The catalyst really provides an alternative path for transformations in which we require activation energy is less. Lesser activation energy permits larger amount of reaction in given time. The catalyst does not affect the final state of equilibrium. Now, temperature and reactions rate. The Arrhenius equations. Temperature has profound influence on the reaction velocity in homogeneous thermal reactions. For every 10 degree rise in temperature, the velocity of reaction is doubled or tripled. The ratio is called temperature coefficient, that is Kt plus 10 upon Kt is 2 or 3. Arrhenius 1889 showed the velocity constant K of chemical processes increases exponentially with the temperature for large number of reactions. It was observed that the plot log K against given a linear equation. He therefore suggested empirically the relation D in K, D upon dt is equal to E upon RT square, or K equal to AE minus E upon RT, A equal to constant. A is called the frequency factor of pre-exponential factor, E is the called of activation energy of reactions. These two quantities have definite value for any given reaction. By measuring the velocity constant K and K dash are two temperatures T and T dash respectively. We have hence the activation energy is easily obtained. Alternative, a plot of log K against 1 by T gives a straight line. The slope of such lines gives the value of E upon 2.303 R, from which E is evaluated. The intercept of line, which also enables one to find out the value of frequency factor, is suppose K1 and K2 are the velocity constant of two opposite directions of a reversible process at temperature T. A K1 upon KT B in K1 is equal to minus E1 upon RT plus in A1 constant. In K2 is equal to minus E2 upon RT plus in A2 constant. Subtracting this, now but K1 upon K2 is equal to K equilibrium constant of the reactions, and in K E2 minus E1 RT plus in A1 upon A2, where E1 and E2 are the activation energy of two opposite processes. Hence D in K upon dt is equal to minus E2 minus E1 upon RT1, that is E minus 1 minus E2 upon RT square. From Van 't Hoff equation, D in K upon dt, del H is equal to del H upon RT square, where del H is the heat change of the chemical process. Comparing two expressions, we get del H is equal to E1 minus E2. Activation energy of a reactions, its significance. The average energy of reactant is represented by EA and that of resultant by EB. But if A is greater than EB, then the reactant A will not be straight transformed to the product B. There is a minimum energy level of reactions denoted by EX, to which the reactant molecules must be raised in order to enable it to undergo the chemical change. The excess of or additional energy EX minus EA which reactant must require in order to undergo transformation, the activation of energy E1. Molecules have energy Ex or above said to be activated state, and such molecules only fit for chemical reactions. If E2 is greater than E1, the reactions is evidently exothermic, whereas if E2 is smaller than E1, the reaction is endothermic. Collision theory. The collision theory explains the mechanism of bimolecular reactions, but with unimolecular reactions, the theory apparently fails. In unimolecular reactions, which are also first order, only one molecule take parts in the reaction. According to Lindemann hypothesis, the molecules acquire activation energy through collision, but the activated molecules decomposes only when after some time has elapsed after collision. That is, there is a time lag between the moment of activation and the moment of decomposition. When this time lag is relatively large, there is every possibility of for most activated molecules being deactivated by subsequent collision to ordinary molecules. As a result, the rate of decomposition will not be proportional to all activated molecules, but only a fraction which survive the time lag. The activated molecules therefore disappears through two parallel processes, namely through deactivation and through decomposition. A first, that is A plus A K in the presence of K1, that is A plus A star. Rate of deactivation is dCA star upon dt is K1 upon C2A. Next is A star plus A, that is K2 upon 2A. Rate of deactivation minus dCA upon dt is equal to K2 CA C star A. Third, A star K3B plus products of rate of decomposition minus dC star A dt is equal to K3 C star A, where A represented ordinary and A star activated molecules. The rate of reactions, a rate in which products are formed, is minus dC upon dt is equal to dCB upon dt is equal to K3C star A. Now, activated molecules are short-lived, have a small concentration of any time during in the process. So from the steady state principle, the rate of formation of A star molecules and the rate of disappearance would be same. Now, case 1, when the rate of deactivation is very large compared to the decomposition, when K2Ca is greater than K3, which is expression of the first order kinetics. Case 2, when concentration Ca is lowered considerably, the changes of deactivation by collision decrease largely. K3 greater K2Ca, when hence we have thus had a low concentration process would follow the order kinetics. Transition state theory. According to this theory, two reactants AB and AC form a transition complex which compose into BA and BC. Now, the basic idea that we must force C to come close to B and B becomes undecided as to which have atoms belongs to. This is a state of indecision as to B being simultaneously attached to both A and C. Thus, somehow usually then before is this transition state, also called the activated complex. The energy necessary to push to C to approach B to form transition state or activated complex in the energy activation. The observed rate of reactions would be equal to the net rate of formation of the activated complex.
This is all from this video. Thank you so much for watching.